Hello there, and welcome to the Dreamy Ocean Channel. Allow your breath to deepen now, settling into a rhythm as gentle as the tide. Unclench your jaw, release the tension from your shoulders, letting your body become heavy soft and at peace, preparing for a descent not of the body, but of the mind. Have you ever truly considered the profound mystery of what lies at the absolute end of all falling? What silent stories are whispered by the deepest trenches of our world, where light never reaches and gravity holds an eternal, unwavering vigil? What forgotten echoes, what strange remnants, what untold histories lie, cradled in the profound darkness of Earth's ultimate abyss, the Mariana Trench. It is a place where the crushing weight of water guards secrets beyond our immediate comprehension, a realm where everything eventually descends, accumulating over eons. Tonight, as the world outside begins to hush, allow your consciousness to sink with us gently into these profound depths, letting the whispers of the trench guide you towards a tranquil sleep. The abyssal cradle of Earth, far across the vast blue expanse of the western Pacific Ocean, where the sun's golden light shimmers upon endless waves, lies a profound incision in the very crust of our planet. It is a crescent-shaped scar stretching for more than 2,500 kilometers, a silent gaping maw in the ocean floor. This is the Mariana Trench, a geological wonder, not merely a deep canyon, but a monumental furrow carved into the earth, a place of ultimate descent, a true abyssal cradle. Here, the very concept of depth transcends simple measurement, becoming instead a gateway to an alien realm utterly detached from the familiar surface world. The formation of this colossal chasm is a story told in the slow, inexorable grind of tectonic plates, a ballet of continental masses moving with an ancient, unhurried grace. For countless eons, the immense Pacific Plate, a colossal segment of Earth's lithosphere, has been relentlessly sliding ever so slowly beneath the smaller Mariana Plate. This geological process, known as subduction, is the engine that sculpts the deepest features of our world. Imagine one vast, rigid slab of rock, denser and heavier, yielding to an unseen force, beginning its long, deliberate plunge back into the Earth's molten mantle. As it descends, it pulls the overlying crust downward, creating this elongated, profound valley, a colossal furrow in the ocean floor. It is a process that has unfolded over tens of millions of years, an ongoing, subtle tectonic sigh that continues even now, deepening the trench millimeter by slow millimeter. Within this elongated depression at its southern end lies its most profound point, the Challenger Deep. This specific basin, a smaller, even more intense depression within the Greater Trench, plunges to an astonishing depth of approximately 11,000 meters below the ocean's surface. To truly grasp this immense scale, consider the highest mountain on Earth, Mount Everest, its snow-capped peak piercing the thin air at nearly 9,000 meters. If Everest were inverted and placed within the Challenger Deep, its summit would still be submerged by more than 2 kilometers of water, an unimaginable volume pressing down from above. This is not merely deep, it is the very extreme edge of our planetary surface, a boundary where the familiar rules of our world begin to warp and stretch under an immense, suffocating pressure. This crushing pressure is perhaps the most immediate and defining characteristic of the trench. At the level of the Challenger Deep, the water exerts a force of over 1,000 times atmospheric pressure, a staggering 110 million pascals. To visualize this, imagine the weight of 50 jumbo jets, each a leviathan of steel and fuel, balanced precariously upon a single human thumb. Every square centimeter of surface at that depth endures this unimaginable burden, a relentless, pervasive force that sculpts and compresses everything within its grasp. It is a pressure that would instantly crush most man-made objects, collapsing even the strongest steel hulls like crumpled foil, a testament to the sheer power of the water column above. Only specialized submersibles crafted with meticulous precision and extraordinary materials can withstand this silent, omnipresent squeeze. Our initial tentative understanding of this abyssal realm began not with direct observation, but with the painstaking work of early oceanographers. It was during the HMS Challenger expedition, a pioneering scientific voyage spanning the years 1872 to 1876, that humanity first truly glimpsed the existence of such profound depths. Using rudimentary-sounding lines, long ropes weighted with lead, and painstakingly lowered into the ocean, the crew of the Challenger recorded the first measurements of what would later be recognized as the Mariana Trench. These early soundings, though less precise than modern sonar, revealed depths far exceeding any previously known, hinting at a world utterly unlike anything imagined. It was a slow, laborious process, each measurement taking hours, but it unveiled a silent, staggering truth: our planet held secrets far deeper than anyone had dared to dream. The environment of the Mariana Trench is one of perpetual twilight, fading quickly into absolute inky blackness. Sunlight, which nourishes the vibrant ecosystems of the surface, cannot penetrate beyond a few hundred meters. Below that, the ocean becomes a realm of eternal night, illuminated only by the occasional bioluminescent flash of a deep-sea creature, or the faint ghostly glow of a hydrothermal vent. Temperatures at these depths hover just above freezing, typically between 1 and 4 degrees Celsius, a chilling embrace that adds to the alien nature of the environment. The water itself is dense and still moving, with currents so slow and ancient they seem almost suspended in time, carrying only the most subtle whispers of the world above. This profound stillness, combined with the extreme pressure and cold, creates a unique preservation chamber, a natural archive where the passage of time is measured in geological epochs rather than human years. This slow, deliberate process of subduction, the immense pressure, the eternal darkness, and the chilling temperatures all contribute to making the Mariana Trench a literal, abyssal cradle. It is a place designed by geological forces to collect and hold a repository for whatever descends into its depths. Unlike shallower ocean basins where currents are more active and geological activity might redistribute sediments more frequently, the trench acts as a natural trap. Its steep, confining walls and its incredible depth mean that once something reaches its floor, it is largely isolated from the dynamic forces that shape the rest of the ocean. It becomes a permanent resident, slowly becoming encased in layers of fine sediment, a silent witness to the passage of time. The very nature of its formation, the slow, yielding descent of one plate beneath another, creates an environment where material can accumulate with minimal disturbance. Over millions of years, countless particles, both organic and inorganic, have drifted down, settling upon the trench floor. Each grain of sediment, each microscopic organism, each larger fragment that finds its way into this ultimate abyss adds to the growing layers that form its bedrock. It is a continuous, gentle rain of particles, a slow accumulation that builds up the history of our planet layer by silent layer. The Mariana Trench, therefore, is not merely a geological feature. It is a profound collector, a deep-sea vault silently gathering the fragments of worlds, both ancient and modern, holding them in its cold, dark embrace, awaiting discovery or perhaps simply eternal rest. Its very existence speaks of a deep, patient earth constantly reshaping itself, creating these ultimate resting places where the stories of what falls are preserved in the profound quiet. The crushing embrace of the deep. The very essence of the Mariana Trench, beyond its sheer staggering depth, is defined by an invisible, omnipresent force, the crushing embrace of hydrostatic pressure. As we descend, moving through the water column, each passing meter adds another subtle layer of weight, a cumulative burden that becomes truly monumental at the ocean's floor. This pressure is not a sudden, violent impact, but rather a slow, relentless squeeze and unyielding compression that permeates every atom, every molecule, every living cell within its grasp. It is the silent, pervasive hand of gravity pulling an entire ocean downward, focusing its immense weight upon the trench's dark, waiting heart. To comprehend this force, we must consider the nature of water itself. Water, though seemingly fluid and yielding at the surface, is in fact a dense and heavy substance. Imagine a column of water, a liquid pillar stretching 11,000 meters from the sunlit surface to the abyssal plain. Each cubic meter of this water weighs approximately 1,000 kilograms, a metric ton of liquid mass. Now multiply that by the immense vertical distance, and the sheer volume above any point in the Challenger Deep becomes almost unfathomable. This colossal weight is distributed evenly across every surface, pressing inward from all directions, a truly isotropic force. It is not like being crushed by a single heavy object, but rather like being submerged within a solid, invisible medium that seeks to reduce all voids to compress all forms into their most compact state. This profound pressure, reaching over 1,000 times the atmospheric pressure we experience at sea level, fundamentally alters the physical and chemical landscape of the deep ocean. For most life forms adapted to the gentle pressures of shallower waters, such a descent would mean instant catastrophic collapse. Gas-filled organs like swim bladders in fish would implode. Cellular structures delicate and finely tuned would distort and cease to function. Proteins, the intricate molecular machinery of life, would denature, losing their precise three-dimensional shapes, unraveling like a delicate thread in a tempest. Yet life persists in the trench, not merely surviving, but thriving, a testament to evolution's ingenious ability to adapt to the most extreme conditions. The organisms that call the Mariana Trench home, known as piezophiles or pressure lovers, possess extraordinary adaptations at a molecular level. Their proteins, the fundamental building blocks and catalysts of their biological processes, are structured differently. They are more rigid, more compact, designed to maintain their functional integrity even under immense compression. Think of them as tiny molecular fortresses precisely engineered to resist the relentless inward push. Furthermore, these deep-sea inhabitants often produce specialized organic molecules called osmolytes, such as trimethylamine N-oxide or TMAO. These small, soluble compounds act as molecular chaperones, shielding the delicate proteins from the denaturing effects of high pressure. They prevent the water molecules under such extreme squeeze from disrupting the vital hydrogen bonds and hydrophobic interactions that give proteins their essential shape and function. It is a subtle internal battle won by the quiet resilience of these specialized biochemical agents. Beyond the biological, the crushing embrace of the deep also profoundly impacts the materials we send into this alien realm. For human exploration, designing vehicles capable of withstanding such forces is an immense engineering challenge, a constant battle against the ocean's relentless desire to reclaim all space. Traditional materials like steel, which is strong under tension, can buckle and crumple under the immense uniform compression of the deep. Submersibles, therefore, are often designed with spherical pressure holes, as a sphere is the most geometrically efficient shape for distributing external pressure evenly across its surface, minimizing stress concentrations. Materials like high-strength titanium alloys or even thick, meticulously cast acrylic glass are employed, each chosen for its ability to resist the implacable squeeze. The very concept of implosion is a stark reminder of the trench's power. Unlike an explosion where forces push outward, an implosion is an inward collapse, a sudden violent act where the external pressure overwhelms the structural integrity of an object, crushing it into a fraction of its original volume. For a submersible, even a tiny flaw, a microscopic crack, could initiate such a catastrophic failure as the surrounding water rushes in to fill the void with unimaginable speed and force. It is a constant whisper of danger for those who dare to venture into these profound depths, a silent warning of the immense power held by the ocean. Even the very chemistry of the deep ocean is subtly altered by this crushing pressure. The solubility of gases, for instance, changes significantly. Carbon dioxide, when subjected to such immense forces, becomes far more soluble in water, dissolving readily into the deep ocean. This has implications for the global carbon cycle, as the deep ocean acts as a vast, slow sink for atmospheric CO2. Chemical reaction rates can also be affected, with some reactions slowing down and others accelerating, as the increased proximity of molecules under pressure alters their energetic interactions. The water itself, though still liquid, becomes slightly denser, its molecules packed more tightly together, a subtle yet pervasive transformation of its fundamental properties. The journey into this crushing embrace is a descent into a world where familiar concepts are redefined. Sound travels differently, often faster through the denser water, and light, as we know, is utterly extinguished. What remains is a realm of profound silence, punctuated only by the distant creaks of a submersible hull or the faint biological clicks of unseen creatures. It is a world where pressure is not merely a number on a gauge, but a palpable physical presence, an invisible hand that shapes every form, every life, every moment. It is the ultimate test of resilience, both for the life that evolved within it and for the human ingenuity that seeks to explore its most guarded secrets. As we contemplate this immense force, we begin to understand why the Mariana Trench is not just a geological depression, but a realm of extreme existence where the Earth itself seems to hold everything in its deepest, most profound embrace. Gravity's relentless pull. Beneath the immense silent weight of the ocean, a force far more ancient and pervasive than any current or tide orchestrates a ceaseless downward migration, gravity's relentless pull. It is the fundamental architect of all descent, the quiet, unwavering hand that guides every particle, every fragment, every lost object from the sunlit surface towards the profound, inky blackness of the abyssal plain. While the previous chapter illuminated the sheer crushing pressure of the deep, here we turn our gaze to the journey itself, the slow, deliberate pilgrimage of matter responding to Earth's inexorable attraction, a journey that ultimately culminates in the silent embrace of the Mariana Trench. Imagine for a moment a single microscopic speck of detritus, perhaps a fragment of a dead diatom, a tiny jewel-like organism that once floated in the sun-drenched surface waters. Its life ended, its delicate silica shell, now devoid of its living essence, begins its long, solitary drift downwards. It does not plummet with haste, but rather descends with an almost ethereal slowness, suspended momentarily, then yielding to the faint, persistent tug from below. The water, dense and viscous, offers resistance, a subtle friction, that cradles the tiny particle, slowing its fall. This is the interplay of buoyancy, the upward push of the displaced water against the downward insistence of gravity. For such a small, lightweight entity, the forces are finely balanced, resulting in a descent measured not in seconds, but often in days, weeks, or even months. This slow, continuous rain of organic and inorganic matter from the upper ocean is what oceanographers term marine snow. It is a constant, gentle snowfall in an eternal night, composed of dead plankton fecal pellets, discarded larval casings, and other biological debris, all delicately bound together by sticky mucus-like substances. Each flake of this marine snow, though ephemeral, carries with it nutrients and carbon, a vital link between the vibrant life of the euphotic zone and the starved ecosystems of the deep. As these delicate aggregates drift downwards, they are transformed. Some are consumed by opportunistic grazers in the mesopelagic zone, a twilight world where faint light still penetrates. Others are broken apart by microbial activity, their constituent organic compounds slowly recycled. But a significant portion continues its unhurried descent, a ghostly procession towards the ultimate sink. Larger objects with greater density and mass experience a more pronounced gravitational pull, leading to a somewhat swifter descent. Consider the carcass of a large whale, its immense body no longer sustained by the ocean's buoyancy. Once alive, it moved with magnificent grace. Now, a colossal inert mass, it begins its long, slow fall through the water column. The sheer scale of such an event is astounding. A creature weighing many tons, sinking through kilometers of water, creates what scientists call a whale fall, a sudden, enormous bounty of nutrients for the deep-sea ecosystem. The descent of a whale can take days, its massive form slowly rotating its passage through the water column, displacing untold volumes, leaving a subtle, temporary trail of disturbed water in its wake. This journey is not without its own drama, as scavengers in shallower depths may begin to feast even before the final resting place is reached, consuming flesh, leaving bones to continue their solitary plunge. Human-made objects, often denser and more resistant to decomposition, follow a similar gravity-driven path. A discarded plastic bottle, initially buoyant, may eventually become waterlogged or accumulate enough biofouling, the growth of algae and microorganisms, to overcome its natural buoyancy. Once its effective density surpasses that of the surrounding water, its slow descent begins. A metal container, a piece of fishing gear, or even the remnants of a shipwreck inherently dense will begin to sink almost immediately, their journey governed by their mass shape and the drag exerted by the water. Unlike the delicate marine snow, these objects often retain their form for much longer, their robust structures resisting the slow decay that claims organic matter. The water column itself acts as a vast transformative filter during this slow descent. Temperature and salinity gradients, though subtle, can influence the density of the water, creating layers that might momentarily slow or deflect a falling object. Deep sea currents, though generally much weaker and slower than surface currents, can still exert a gentle lateral push, guiding objects across vast distances before gravity ultimately pulls them down. Yet, within the confines of the Mariana Trench, with its steep, V-shaped profile, these lateral influences are often overcome by the sheer gravitational advantage of its depth. The trench acts like a colossal funnel, drawing in anything that drifts or sinks within its vast catchment area. Once an object enters the gravitational influence of the trench's deepest points, its ultimate destination is almost assured. The timescales involved in this journey are often immense. For the finest particles of marine snow, the descent from the surface to the Challenger Deep can span several months. For larger, denser objects, it might be a matter of days or weeks. But even for the swiftest descents, the deep ocean is a realm where time itself seems to stretch and distort. The journey is not just a physical movement downwards, but a passage through different environmental regimes, from light to darkness, from warmth to cold, from lower pressure to unimaginable compression. Each stage of this journey leaves its mark, altering the object, transforming its composition, or even facilitating its partial decomposition. This relentless gravitational pull is the primary mechanism by which the Mariana Trench accumulates its silent, layered history. It is a constant, unceasing process operating every second of every day across millions of years. Every discarded fishing net, every piece of microplastic, every lost scientific instrument, every fragment of a long-dead creature, and even the most mysterious, unidentified objects are all subject to this same fundamental law. They are drawn inexorably downwards, stripped of their stories in the upper waters, until they settle upon the abyssal floor, becoming part of the trench's ever-growing archive. The trench, therefore, is not merely a hole in the ground. It is the ultimate gravitational trap. A profound repository built by the patient, unwavering hand of Earth's own attraction, preserving the whispers of every single thing that succumbs to the slow, deep descent. Organic rains from above. From the profound, unseen hand of gravity that pulls all matter downwards, a ceaseless, gentle phenomenon unfolds in the vast liquid expanse above the Mariana Trench. A silent, continuous shower of organic material known to oceanographers as marine snow. It is a delicate, ethereal fall, a constant, unhurried precipitation of life's fragments, drifting through kilometers of water, carrying the stories of the sunlit surface world into the eternal night of the deep. This is the primary sustenance for the abyssal realm, a lifeline of nutrients descending from the vibrant, productive upper layers, a whisper of life delivered to the deepest, most desolate corners of our planet. Imagine a world teeming with microscopic life just beneath the ocean's surface. Diatoms, tiny single-celled algae encased in intricate silica shells, float and multiply, harnessing the sun's energy through photosynthesis. Dinoflagellates with their whip-like tails spin through the water. Copepods, small crustaceans, graze upon these phytoplankton, their intricate movements creating subtle currents. All this life in its vibrant cycle of birth, growth, and eventual demise contributes to the genesis of marine snow. When these organisms die, their delicate bodies or parts of them begin their slow surrender to gravity. A dead diatom, its elegant shell now, a hollow vessel, starts its long, solitary drift. A copepod's discarded exoskeleton shed during growth becomes another tiny, shimmering flake. But marine snow is more than just individual dead cells. It is a complex flocculent aggregate, a sticky living blizzard. Fecal pellets rich in undigested organic matter from grazing zooplankton are a major component, often sinking much faster than individual cells due to their denser, more compact nature. These pellets are miniature packages of nutrients designed by biology to efficiently transport carbon and energy downwards. Then there are the mucus webs secreted by gelatinous plankton like appendicularians, which filter vast quantities of water, trapping smaller particles. When these delicate, translucent webs are abandoned or break apart, they too become part of the descending snow, acting as natural glues, binding smaller fragments together into larger, faster sinking clumps. It is a dynamic, ever-changing composition reflecting the intricate web of life that thrives in the sunlit zone above. The journey of marine snow is an odyssey of extreme slowness, a testament to the water's viscosity and the delicate balance of forces at play. Each aggregate, whether a single dead cell or a composite clump, begins its descent with an almost imperceptible yield to gravity. It does not plummet, but rather drifts, spirals and tumbles with an unhurried grace like dust motes caught in a shaft of sunlight, but in a medium far denser and more resistant. The water, cold and dark, offers a persistent drag, cradling each particle, slowing its fall, to a pace that can take days, weeks, or even months for a single flake to traverse the kilometers from the surface to the abyssal plain. This extended journey is crucial as it allows for a gradual transformation of the snow itself. As the marine snow descends through the vast water column, it undergoes a continuous process of alteration and consumption. In the mesopelagic zone, the twilight zone extending from about 200 to 1,000 meters, where only the faintest blue light penetrates, opportunistic creatures lie in wait. Lanternfish, bristlemouths, and various jellyfish are adapted to intercept this falling manna. They filter, graze, and consume the descending particles, breaking down the aggregates, recycling some of the organic matter back into the mid-water ecosystem. Bacteria and other microorganisms also play a vital role, colonizing the surfaces of the snow particles, slowly decomposing the organic compounds, releasing dissolved nutrients back into the water, and transforming the chemical signature of the snow as it continues its long, patient fall. This constant biological processing means that only a fraction of the organic carbon produced at the surface actually reaches the deepest parts of the ocean. Yet despite this continuous consumption and decomposition, a significant portion of this organic rain does indeed reach the abyssal depths, including the Mariana Trench. The trench, with its deep, confining structure, acts as a particularly efficient collector of this precious snowfall. The steep walls funnel the descending particles towards its deepest point, concentrating the organic matter in a way that shallower, more expansive abyssal plains might not. When these delicate flakes finally settle upon the trench floor, they form a soft, flocculent layer, a nutrient-rich blanket that is the literal foundation for the unique ecosystems thriving in this extreme environment. This layer, often described as a fine, silty ooze, is composed not just of organic detritus, but also the skeletal remains of silica and calcium carbonate from diatoms and foraminifera, creating a complex layered sediment. For the life forms inhabiting the Challenger Deep, this organic rain is their very sustenance. In a world devoid of sunlight, where photosynthesis is impossible, the primary source of energy comes from above. Deep-sea amphipods like the tiny pale Hirondelia gigas crawl across the sediment, sifting through the fallen particles, extracting vital nutrients. Holothurians or sea cucumbers slowly move across the abyssal plain, ingesting the organic-rich mud, acting as living vacuum cleaners, processing the marine snow and returning inorganic matter to the environment. Specialized bacteria and archaea decompose the more resistant organic compounds, releasing energy and nutrients that can then be utilized by other organisms further up the deep-sea food web. The entire ecosystem of the trench is thus intricately linked to this ceaseless, gentle shower from the sunlit world, a testament to the interconnectedness of all life on Earth, even across vast, lightless distances. The rate at which marine snow accumulates in the trench is incredibly slow, a process measured in millimeters per 1,000 years. This slow deposition, combined with the extreme conditions of cold, high pressure, and often low oxygen levels, contributes to the remarkable preservation of some organic materials. While much of the readily decomposable organic matter is consumed or broken down, more resilient compounds can persist for extended periods, slowly becoming incorporated into the accumulating layers of sediment. These layers become a geological archive, a silent record of past oceanic conditions, past surface productivity, and even past climatic events. Scientists, by carefully analyzing these sediment cores, can reconstruct environmental histories stretching back hundreds of thousands, if not millions of years, reading the story etched in the compressed layers of ancient marine snow. Thus, the shower of snow is not merely a passive phenomenon. It is a dynamic, vital process, a fundamental component of the ocean's biogeochemical cycles. It represents the biological pump, the downward transport of carbon from the atmosphere and surface waters to the deep ocean, playing a crucial role in regulating Earth's climate over geological timescales. Each tiny drifting flake, each flocculent aggregate participates in this grand planetary scale process, a testament to the profound and often unseen connections that bind our world together. As these gentle, organic rains continue their eternal descent, they remind us that even in the deepest, most remote parts of our planet, life finds a way sustained by the quiet, unhurried gifts from above, falling softly into the abyssal cradle of the Mariana Trench. Plastic's deepest scar. While the delicate, ephemeral flakes of marine snow drift downwards, whispering tales of life and decay from the sunlit surface, carrying vital nutrients to the starved ecosystems below. Another, far more enduring precipitation now joins this ancient descent. This new rain is not born of nature's cycle, but of human ingenuity, a testament to our profound, pervasive influence upon the planet. It is the rain of plastic, a synthetic snowfall that settles upon the deepest floors, leaving an indelible scar, a silent, persistent whisper of the Anthropocene in Earth's most remote and untouched depths. Plastic, in its myriad forms, began as a marvel of modern chemistry. Light, durable, versatile, and inexpensive, it revolutionized countless aspects of human life, from packaging to clothing, from construction to medicine. Yet these very properties, its incredible persistence and resistance to natural degradation, have become its most profound curse in the natural world. Unlike organic matter, which yields to the patient work of decomposers, slowly returning its constituent elements to the grand cycle of life, plastic remains a stubbornly eternal artifact. Its molecular bonds, forged by human design, resist the enzymes of bacteria and fungi, defying the natural processes of decay that govern virtually all other materials on Earth. The journey of plastic into the deep ocean is often a slow, circuitous one. Many plastics initially are buoyant, floating upon the ocean's surface for weeks, months, or even years, carried by currents across vast distances, becoming silent, colorful wanderers. A discarded bottle, a fragment of fishing line, a forgotten grocery bag. Each begins its journey in the sunlit world. But slowly, imperceptibly, microscopic organisms begin to colonize its surfaces. Algae, bacteria, and tiny invertebrates attach themselves, forming a living film known as biofouling. As this biological layer thickens, it adds weight, gradually increasing the overall density of the plastic object. Eventually, for many types of plastic, this added weight overcomes its natural buoyancy, initiating its long, unhurried descent into the darker, colder realms below. Other plastics inherently denser than seawater, such as PVC or PET, begin their downward journey almost immediately upon entering the ocean, sinking directly towards the abyssal floor. As these synthetic fragments drift downwards, they pass through the same vast, crushing water column that marine snow traverses. Yet, unlike the delicate organic aggregates, plastic resists transformation. It does not readily decompose, nor is it easily consumed by the mid-water scavengers that filter the natural falling detritus. Instead, it maintains its form, slowly becoming a permanent fixture of the deep. Even the extreme pressures of the Mariana Trench, which can reshape metal, do not fundamentally break down the chemical structure of most plastics. Instead, they might cause physical fragmentation, splintering larger pieces into smaller ones, but the underlying polymer chains remain intact, merely parceled into tinier units. The first definitive discoveries of plastic within the Mariana Trench were a sobering realization of humanity's pervasive reach. Expeditions utilizing remotely operated vehicles, or ROVs, designed to explore the deepest, most inaccessible parts of our planet, began to capture images and samples that revealed an unexpected, incongruous presence. In 2017, a scientific review compiling data from over 5,000 deep-sea submersible dives and ROV deployments found plastic debris in every major ocean trench, with the highest density recorded in the Mariana Trench. A plastic bag, a familiar mundane object from our daily lives, was observed at a staggering depth of 10,900 meters in the Challenger Deep, a stark, silent sentinel of our surface world's careless abundance. These finds were not isolated incidents. Subsequent missions have continued to document a persistent, widespread presence of plastic, from recognizable items to microscopic fragments scattered across the abyssal plains and clinging to the trench walls. The types of plastic found within the trench reflect the dominant forms of plastic pollution originating from human activity. Single-use plastics such as plastic bags and food wrappers are frequently observed. These items, lightweight and easily carried by wind and currents, are particularly prone to entering the marine environment. Fishing gear, often referred to as ghost gear, when lost or abandoned, constitutes another significant component. Derelict fishing nets, lines, and traps made from durable synthetic polymers continue to ghost fish for decades or even centuries, entangling marine life and slowly sinking into the deep. But perhaps most insidious are the microplastics and nanoplastics, tiny fragments less than 5 millimeters in size, often invisible to the naked eye. These microscopic particles result from the physical breakdown of larger plastic items over time, or are directly introduced into the environment from sources like synthetic clothing, fibers, or microbeads in cosmetics. The implications of this plastic pollution for the deep-sea ecosystems of the Mariana Trench are profound and still being fully understood. The trench, once considered a pristine, isolated realm, is now directly impacted by human waste. Deep-sea organisms exquisitely adapted to their unique environment are encountering these alien materials. Studies have revealed that amphipods, small crustaceans that scavenge the trench floor, have ingested microplastic particles. Their delicate digestive systems, designed to process marine snow and organic detritus, are now burdened with indigestible synthetic fragments. The chemical additives within plastics such as phthalates and bisphenol A known endocrine disruptors can leach into the surrounding water, potentially impacting the physiology and reproduction of deep-sea life in ways we are only beginning to comprehend. Furthermore, ghost fishing gear poses a direct physical threat, entangling and suffocating creatures in the dark, cold waters, continuing its destructive work long after being discarded by human hands. The Mariana Trench, with its immense depth and confining structure, acts as a global sink for this plastic debris. Once plastic enters the trench, its chances of escape are virtually non-existent. The steep walls, the crushing pressure, and the slow, deep currents ensure that anything that falls into its abyssal embrace becomes a permanent resident. It is a one-way journey, a final resting place where plastic will accumulate for millennia, slowly becoming incorporated into the geological record, a distinct, enduring layer marking the human epoch. This accumulation transforms the trench from a pristine natural archive into a vast deep-sea landfill, a somber testament to our civilization's consumption and disposal patterns. This presence of plastic in Earth's deepest place is more than just an environmental concern. It is a profound symbolic statement. It whispers of the Anthropocene, the proposed geological epoch, defined by the dominant impact of human activities on Earth's geology and ecosystems. The plastic found in the Mariana Trench is an undeniable physical marker of this new age, a geological signature that will persist for millions of years long after our species has passed. It is a permanent scar etched into the very deepest part of our planet, a silent, enduring testament to the far-reaching consequences of our actions, even in realms we barely understand. As these synthetic fragments continue their slow, unhurried descent, settling upon the abyssal floor, they become part of the trench's evolving story, a story that now inextricably links the ancient, patient Earth with the fleeting yet impactful presence of humanity. Sunken legacies. While the pervasive synthetic fragments of plastic now form a distinctive, enduring layer within the abyssal sediments, a silent testament to our modern age, other more substantial echoes of humanity also find their way into the profound depths. These are the sunken legacies, the larger, more robust artifacts of human endeavor, and tragedy objects that carry with them the weight of history, the stories of ambition, exploration, and sometimes profound loss. These remnants, from the colossal hulls of ships to the intricate machinery of lost scientific probes, and even the remnants of objects that once soared through the vacuum of space, embark on their slow, final descent, ultimately yielding to gravity's relentless pull, finding their eternal resting place within the crushing embrace of the Mariana Trench. Consider for a moment the fate of a great vessel, a ship of steel and purpose navigating the vast, often unforgiving surface of the Pacific. Through storm accident or conflict, its structural integrity might be breached, water rushing in with unstoppable force, overwhelming its buoyancy. The ship, once a proud silhouette against the horizon, begins its slow, inexorable plunge. This is not a sudden drop, but a protracted, often dramatic descent, a battle between the remaining air trapped within its compartments and the invading, crushing weight of the ocean. As it sinks, the increasing pressure acts upon its hull, bending and tearing metal, imploding sealed spaces with terrifying internal force. Windows shatter, bulkheads crumple, and the very form of the vessel begins to distort, reshaped by the ocean's immense squeeze. Once it reaches the pitch-black depths far beyond the reach of light or human rescue, it settles upon the abyssal floor, a colossal, silent monument to its past, a permanent guest in the trench's dark, cold embrace. The deep ocean, and particularly the extreme conditions of the Mariana Trench, offers a unique environment for the preservation of these sunken legacies. Unlike wrecks in shallower, oxygen-rich waters where active currents and a bustling community of decomposers rapidly break down organic materials and corrode metals, the abyssal environment is a realm of profound stillness and slow decay. Oxygen levels are often extremely low, sometimes almost anoxic, stifling the metabolic activity of many aerobic bacteria that would otherwise consume organic matter. Temperatures hover just above freezing further, slowing down chemical reactions and biological processes. The absence of light means no photosynthetic organisms, and thus a greatly reduced food web compared to the surface. In this cold, dark, high-pressure realm, the processes of corrosion and decomposition are dramatically decelerated, allowing objects to persist for centuries, even millennia, in a remarkably preserved state. A wooden beam from a ship, for instance, might endure for far longer than it would in temperate coastal waters, slowly becoming impregnated with minerals, transforming into a dense, waterlogged relic. Beyond grand shipwrecks, a myriad of smaller yet equally significant human artifacts also find their way to the deep. Lost scientific instruments, perhaps a deep-sea sensor array that detached from its mooring, or a remotely operated vehicle that suffered a catastrophic failure, can plummet into the trench. These are not mere pieces of debris. They are intricate machines designed to probe the very mysteries of the deep, now themselves becoming part of the mystery. Their advanced materials, often titanium-specialized alloys or reinforced polymers, are engineered to resist the very forces they now succumb to, offering a glimpse into the limits of human technology when confronted with the raw power of nature. Each lost probe, each fallen sensor represents a small fragment of our collective scientific ambition, a silent testament to our unyielding quest for knowledge. The military, too, has inadvertently contributed to the trench's growing collection. During times of conflict or training exercises, aircraft can crash into the ocean, their heavy components sinking rapidly. Submarines designed to withstand immense pressures can suffer catastrophic failures, imploding as they descend, their fragmented remains scattered across the abyssal plain. Munitions from unexploded bombs to discarded torpedo casings robustly constructed of metal also settle into the deep. These are grim reminders of human conflict now resting in eternal silence, their destructive potential neutralized by the ocean's overwhelming power, slowly becoming encrusted with manganese nodules and deep-sea sediments. These objects, often made of dense, resistant materials, are among the most likely to reach the very deepest parts of the trench, their metallic forms enduring for vast stretches of time, slowly corroding but always present. Yet not all human legacies descend from the ocean's surface. Some arrive from an even greater distance, from the cold, silent void of space itself. For decades, certain regions of the deep ocean, far from shipping lanes and human habitation, have been designated as controlled impact zones for decommissioned satellites, rocket stages, and even entire space stations. These colossal pieces of engineered metal, having survived a fiery re-entry through Earth's atmosphere, plummet with immense velocity into the water. Their impact a momentary distant thunder in the deep. The South Pacific Ocean uninhabited area, often referred to as the spacecraft cemetery, is one such region where fragments of human ambition forged for the stars ultimately find their final watery grave. While the Mariana Trench is not the primary target for such controlled re-entries, the sheer scale of global space launches means that stray debris or fragments from uncontrolled re-entries can, and do, find their way into any part of the vast ocean, including its deepest trenches. These are the ultimate exotic echoes of humanity, celestial debris returning to Earth, settling into the abyssal cradle, a cosmic dust from our own technological endeavors. And in the profound quiet of the deep, even the transient forms of organic life, including those of our own species, eventually yield to the ocean's transformative embrace. While the immediate fate of soft tissues in the oxygen-starved depths is decomposition, albeit at a greatly decelerated pace. Compared to surface waters, the denser, more resilient structures like bone can persist for far longer. In the extreme cold and pressure, with limited scavenging activity for large carcasses, these skeletal remnants, stripped of their stories, become part of the trench's silent sediment, slowly encased, a poignant, almost imperceptible whisper of a life that once was. It is a natural process of the deep ocean's transformative power, a return to the earth from which all life springs a final, quiet dissolution into the vast, ancient cycles of the planet. These sunken legacies, whether they be the grand skeletons of ships, the intricate remains of scientific probes, the silent reminders of conflict, or the exotic fragments of space exploration, all contribute to the Mariana Trench's identity as a unique deep-sea archive. Each object, once imbued with human purpose, now lies in profound stillness, slowly becoming a geological artifact, a time capsule preserved by the very forces that brought it there. They are not merely trash in the conventional sense, but rather silent witnesses to our history, our advancements, and our vulnerabilities. They tell a story of human reach, extending from the surface of our planet to the void of space, and ultimately to the deepest, darkest corners of our own world. As these echoes settle, layer by silent layer, they become an enduring part of the Trench's evolving narrative, a testament to humanity's indelible mark on the Earth's most remote and profound landscapes. Feast or famine, as the echoes of humanity's deepest imprints settle into the Trench's silent sediment. A profound and ancient narrative continues to unfold within this ultimate abyss. The story of life itself, tenacious and extraordinary, clinging to existence in a realm defined by overwhelming pressure, eternal darkness, and the stark dichotomy of feast or famine. This is a world where survival is an art honed over eons, where every metabolic process, every cellular structure, every sensory adaptation is a testament to the ingenious resilience of biology in the face of the most extreme conditions our planet has to offer. The baseline reality for life in the Mariana Trench is one of perpetual, pervasive scarcity. Sunlight, the ultimate fount of energy for nearly all life on Earth, cannot penetrate beyond a few hundred meters, leaving the deep ocean in a state of absolute, inky blackness. Without photosynthesis, there are no plants, no algae to form the vibrant base of a food web. Instead, the primary energy source for the trench floor is the slow, continuous descent of marine snow, those delicate, ephemeral aggregates of organic detritus we previously explored. This gentle, unhurried rain of dead plankton, fecal pellets, and discarded biological fragments represents a constant yet incredibly sparse trickle of nutrients. Imagine living in a desert where sustenance arrives not as a river, but as individual, widely scattered grains of sand, each holding a minuscule promise of energy. The journey of these particles from the surface can take weeks or months, and much of their nutritional value is consumed or decomposed by microorganisms in the upper water column before they ever reach the abyssal plane. This creates a fundamental challenge for any organism seeking to thrive here: how to extract enough energy from such meager, widely dispersed offerings. Yet within this vast, dark expanse of persistent famine, there are rare, episodic moments of extraordinary abundance, sudden, colossal feasts that reshape the local ecosystem for decades. These are the whale falls, the immense carcasses of whales, once magnificent rulers of the surface waters, now succumbing to gravity's pull and sinking to the abyssal floor. A single whale fall can introduce tons of organic carbon to an otherwise starved environment, providing a banquet of unprecedented scale. The arrival of such a colossal food source triggers a rapid, dramatic response from the deep-sea community. Mobile scavengers like immense amphipods and hagfish quickly converge, drawn by the chemical plumes emanating from the decaying flesh. They feast upon the soft tissues, consuming vast quantities, growing larger and reproducing more rapidly than their more sparsely fed counterparts elsewhere. This initial stage of decomposition, driven by the sheer availability of food, can last for months or even years. As the easily accessible flesh is consumed, the whale fall transitions into a new phase. Specialized organisms, particularly bone-eating worms of the genus Osedax, often called zombie worms, begin their remarkable work. These worms, lacking mouths and digestive tracts instead, grow intricate root-like structures that bore into the whale's bones, extracting lipids and proteins. They host symbiotic bacteria within their bodies that help them digest these complex compounds, converting the bone into usable energy. This stage can last for decades, sustaining a unique community of invertebrates, including various snails, crustaceans, and polychaetes, which thrive on the byproducts of the Osedax worms and the remaining organic material within the bones. Finally, after many decades, only the mineralized skeleton remains, slowly becoming encrusted with manganese nodules, and deep-sea sediment a lasting monument to a transient feast. Beyond these rare, spectacular events, another more consistent source of energy exists in certain deep-sea environments, though it is less common in the deepest parts of the Mariana Trench itself, particularly the Challenger Deep. This is chemosynthesis, a process that harnesses chemical energy rather than light. In areas where hydrothermal vents or cold seeps occur, specialized bacteria and archaea oxidize chemical compounds such as hydrogen, sulfide methane, or ion-releasing energy that can then be used to fix carbon dioxide into organic matter. These chemosynthetic microbes form the base of vibrant, often dense localized ecosystems, supporting unique communities of tube worms, clams, mussels, and shrimp, all thriving in the absence of sunlight. While active hydrothermal vents are more prevalent along mid-ocean ridges, and cold seeps occur where hydrocarbons or other fluids seep from the seafloor, scientists theorize that microbial communities in the trench may utilize less dramatic chemical energy sources such as the slow oxidation of minerals in the trench sediments, contributing to the overall abyssal food web. To survive in this world of extreme pressure, cold and limited food, the organisms of the Mariana Trench have evolved an astonishing array of adaptations. At the molecular level, many deep-sea creatures are piezophiles, or pressure lovers. Their proteins are structurally adapted to function optimally under immense compression, resisting the denaturing effects that would cripple proteins from surface-dwelling organisms. They also produce high concentrations of organic osmolytes, such as TMAO, which act as molecular chaperones, stabilizing proteins and preventing water molecules from disrupting their delicate structures under extreme pressure. This internal biochemical engineering allows their cellular machinery to operate efficiently even when subjected to the weight of kilometers of water. Physically, many trench inhabitants lack gas-filled organs such as swim bladders, which would simply implode under the crushing pressure. Instead, they often possess gelatinous water-filled bodies with minimal skeletal structures. The snailfish, for instance, a pale, almost translucent fish, holds the record as the deepest dwelling fish, having been observed at depths exceeding 8,000 meters. Its body is soft and jelly-like, allowing it to withstand the immense pressure without structural damage. These animals have also adapted to the cold, with specialized enzymes that function efficiently at near-freezing temperatures, and often possess high levels of unsaturated fatty acids in their cell membranes, which helps maintain membrane fluidity in the cold. When it comes to coping with famine, the adaptations are equally remarkable. Many deep-sea organisms exhibit extremely slow metabolic rates, conserving energy in an environment where food is scarce. They grow slowly, reproduce infrequently, and often have exceptionally long lifespans, sometimes living for hundreds of years, stretching their limited energy reserves over vast stretches of time. Their senses are often highly developed, particularly chemosensation. Deep-sea amphipods like the Hirondellea gigas, now often referred to by related species such as Eurythenes. Plasticus possess acute chemoreceptors, allowing them to detect the faint chemical signatures of food from great distances, guiding them towards a rare meal drifting down from above. These amphipods are voracious scavengers capable of consuming large quantities of food when available, often storing it in expandable stomachs to sustain them during long periods of scarcity. Other organisms, like the diverse array of deep-sea holothurians or sea cucumbers, are deposit feeders. They slowly traverse the abyssal plain, ingesting vast quantities of sediment, sifting out the sparse organic particles that have settled from the marine snow. Their digestive systems are highly efficient, extracting every last calorie from the nutrient-poor mud. They are the silent gardeners of the deep, constantly processing the seafloor, playing a crucial role in nutrient cycling. The sheer remoteness and extreme conditions of the Mariana Trench also lead to high levels of endemism, species found nowhere else on Earth. Evolution in this isolated crucible has forged unique forms of life, perfectly tailored to their dark, cold, high-pressure world. These are not merely survivors, but thriving inhabitants, each playing a vital role in the delicate, slow-motion ecosystem of the abyss. From the microbial communities that form the base of the food web, patiently breaking down the most recalcitrant organic matter, to the specialized scavengers that capitalize on the rare episodic feasts. Life in the trench is a testament to the boundless adaptability of nature. As we consider these incredible life forms living out their existence in the crushing embrace sustained by the gentle shower of snow and the rare dramatic feasts, we are reminded of the profound interconnectedness of our planet. The vibrant surface waters teeming with photosynthetic life ultimately provide the fundamental energy that sustains the deepest, darkest realms. The Mariana Trench, far from being a barren void, is a living, breathing, albeit slow-motion ecosystem, a testament to life's unwavering persistence. And as these resilient creatures navigate their world of feast or famine, their silent struggles and triumphs unfold beneath kilometers of water, a continuous ancient story of survival in Earth's most extreme cradle. Subduction's deep breath. While the tenacious life of the abyss navigates its world of feast and famine, sustained by the gentle organic rains, from above, the very foundation upon which these creatures dwell is in a state of constant, immense, and slow transformation. The Mariana Trench is not merely a passive receptacle for descending matter. It is the visible scar of Earth's most profound geological engine, a colossal zone where ancient oceanic crust embarks on a journey into the fiery depths of our planet. This is the realm of subduction, a geological furnace where immense forces reshape rock release, trapped waters, and generate the molten breath that rises to form new land, a process that perpetually reworks the very fabric of our world. Imagine the vast Pacific Plate, a segment of Earth's rigid outer shell, stretching for millions of square kilometers, slowly, inexorably sliding beneath the smaller Mariana Plate. This colossal slab of oceanic lithosphere, composed primarily of dense basaltic crust, and the underlying upper mantle is not a uniform, dry mass. Over its immense lifespan, spanning hundreds of millions of years since its formation at distant mid-ocean ridges, this oceanic crust has accumulated a deep blanket of marine sediments. These sediments, a layered archive of marine snow, volcanic ash, and dissolved minerals, are rich in water, both as interstitial fluid, trapped between grains, and more significantly chemically bound within the crystal structures of hydrous minerals. As the Pacific Plate begins its long, patient descent into the Mariana Trench, it carries this vast reservoir of water, both free and bound, deep into the Earth's interior, a silent liquid passenger on a journey into the inferno. The descent is agonizingly slow, measured in centimeters per year, a pace imperceptible to human senses, yet relentless in its geological power. As the plate plunges deeper, the environmental conditions transform dramatically. The crushing embrace of hydrostatic pressure, which we have previously explored in the water column, continues its relentless increase, but now acts upon solid rock. Simultaneously, the temperature begins to rise following the Earth's geothermal gradient. Deeper within the Earth, ambient temperatures climb steadily, reaching hundreds, then thousands of degrees Celsius, a profound heat that emanates from the planet's molten core, and the slow decay of radioactive elements within its mantle. This combination of escalating pressure and rising temperature initiates a series of profound transformations within the subducting slab. The water, initially trapped within the sediments and minerals, becomes the catalyst for these deep-seated changes. As the subducting plate reaches depths of 80 to 150 kilometers, the increasing pressure and temperature force the hydrous minerals, such as serpentinite and chlorite, to undergo metamorphic reactions. These minerals, which incorporate water into their crystal lattices, become unstable under the extreme conditions. In a process known as dehydration, they begin to break down, releasing their chemically bound water. This is not a gentle seepage, but rather a slow, continuous expulsion of superheated fluids, a profound geological sigh deep within the Earth. This released water, now under immense pressure and at high temperatures, is highly buoyant and begins to migrate upwards, permeating the overlying mantle wedge. The triangular block of mantle material situated between the subducting plate and the overriding plate. This ascending superheated water plays a critical role in the generation of magma, transforming the mantle wedge into a geological furnace. The presence of water significantly lowers the melting point of the mantle rock, which is primarily composed of peridotite. Pure, dry peridotite requires extremely high temperatures to melt, far higher than those found in the mantle wedge at these depths. However, when water is introduced, it acts as a flux, weakening the bonds within the silicate minerals, allowing them to melt at much lower temperatures. This process, known as flux melting, is the primary mechanism responsible for generating the vast quantities of magma that characterize subduction zones. The mantle rock, slowly yielding to the transformative power of heat and water, begins to melt, forming pockets of molten rock or magma deep within the Earth. This newly formed magma, being less dense than the surrounding solid mantle rock, begins a slow, arduous ascent towards the surface. It is a buoyant molten breath, pushing its way upwards through fractures and weaknesses in the overriding Mariana Plate. As the magma rises, it can evolve, interacting with the crustal rocks it encounters, assimilating some and undergoing fractional crystallization, where different minerals solidify at different temperatures, altering the magma's composition. Eventually, this molten material breaches the surface, erupting as volcanoes. These volcanic eruptions form long, curving chains of islands known as volcanic island arcs, which typically parallel the deep ocean trench. The Mariana Islands themselves, a beautiful archipelago rising from the Pacific, are a direct manifestation of this deep geological process, the fiery exhalation of Earth's interior, fueled by the water carried down by the subducting Pacific Plate. Each eruption, each plume of ash and lava, is a distant echo of the silent, crushing work being done kilometers beneath the surface. The relentless grind of the subducting plate against the overriding plate also generates immense friction and stress, leading to another powerful geological phenomenon, earthquakes. As the two colossal plates slowly converge and slide past each other, they do not move smoothly. Instead, they lock together in places, accumulating vast amounts of elastic strain energy. When this stress exceeds the strength of the rocks, the plates suddenly slip, releasing the accumulated energy in the form of seismic waves, which we perceive as earthquakes. These tremors can range from subtle vibrations to catastrophic events, capable of generating tsunamis that race across entire ocean basins. The deepest and most powerful earthquakes on Earth often occur within subduction zones, sometimes originating at depths of several hundred kilometers within the subducting slab itself, as minerals undergo phase transformations under extreme pressure, releasing energy in a process known as transformational faulting. The Mariana Trench, therefore, is not merely a quiet cradle. It is also a zone of immense seismic activity, a place where the Earth groans and shudders under the strain of its own internal dynamics. Ultimately, the Mariana Trench, as the entry point of this vast subduction factory, serves as a profound geological sink, a place where not only surface debris, but entire segments of Earth's crust are recycled. While some of the lighter upper sediments are scraped off the descending plate to form an accretionary wedge on the overriding plate, a significant portion of the oceanic crust, along with its deeper sediments and any accumulated human artifacts, including the plastics and other sunken legacies, is carried downwards. This material is slowly consumed, melted, and incorporated back into the Earth's mantle, becoming part of the planet's deep, ancient cycles. This includes the deep carbon cycle, where carbon, both natural and increasingly anthropogenic from plastics, is subducted into the mantle. Over millions of years, some of this carbon can be re-released to the surface through volcanic outgassing, demonstrating a truly long-term planetary-scale recycling process. The Mariana Trench, therefore, is a place of profound geological significance, far more than just a deep hole. It is the active mouth of a massive planetary furnace where the cold, dense skin of the Earth is slowly consumed, transformed by immense heat and pressure, and ultimately recycled. It is where water carried from the surface becomes the key to unlocking the fiery heart of the mantle, generating the molten breath that builds islands and shapes continents. And in this slow, patient, and inexorable process, everything that falls into its deepest embrace, from the most ephemeral marine snow to the most enduring human artifact, is drawn into this grand, ancient cycle, becoming part of Earth's continuous, silent transformation. As we contemplate this deep geological breath, we are reminded of the planet's immense power and its ceaseless internal rhythms, a profound and enduring story unfolding beneath the quiet surface of the ocean. Deep ocean currents. While the Earth's deep interior breathes its fiery molten breath, generating new crust and recycling, oiled through the colossal geological furnaces of subduction zones, the vast liquid expanse above the abyssal plain is also in constant, albeit slow, and often imperceptible motion. Far beneath the familiar wind-driven currents that churn the sunlit surface, waters, an immense global system of deep ocean currents, operates a silent conveyor belt of water, driven by unseen forces of temperature and salinity. These deep currents, moving with a patient, ancient rhythm, play a crucial role in distributing warmth, oxygen, and nutrients across the planet. And in doing so, they subtly influence what ultimately falls into and accumulates within the profound depths of the Mariana Trench. Imagine a hidden liquid river flowing not across a landmass, but through the vast dark canyons and plains of the ocean floor, stretching for thousands upon thousands of kilometers. This is the essence of the thermohaline circulation, often referred to as the Great Ocean Conveyor Belt. Its very name, thermohaline, speaks to its driving forces, thermo for temperature, and haline for salinity, the two properties that primarily determine the density of seawater. Unlike surface currents, which are largely propelled by the friction of wind upon the water, these deep currents are set in motion by differences in water density, a gravitational dance of heavy and light. The genesis of this global conveyor begins in the frigid, high-latitude regions of our planet, particularly in the North Atlantic Ocean and around the Antarctic continent. Here, the biting cold of polar winters chills the surface waters to near freezing temperatures. As ice forms, it preferentially extracts pure water, leaving behind the salt in the remaining liquid. This process increases the salinity of the surrounding seawater, making it significantly denser. This newly formed, exceptionally cold and salty water becomes incredibly heavy, far heavier than the warmer, less saline waters around it. Unable to remain at the surface, it begins its slow, majestic descent, sinking thousands of meters towards the abyssal floor, a process known as deep water formation. This sinking water acts as the powerful initial plunge that drives the entire global circulation system, much like the weight of a heavy object pulling a rope downwards. Once this dense water has sunk to the abyssal depths, it begins its patient multimillennial journey across the vast ocean basins. From the North Atlantic, it flows southward, often hugging the contours of the seafloor, traversing beneath the equator and merging with cold, dense waters formed around Antarctica. This combined abyssal water mass, known as Antarctic bottom water, is the coldest and densest water on Earth, spreading its icy embrace throughout the deepest parts of the Atlantic Pacific and Indian Oceans. It is a slow, methodical creep, a vast, unseen river that fills the deepest troughs and basins, carrying dissolved gases and fine sediments across planetary scales. The speeds of these deep currents are astonishingly slow by human standards, often moving at just a few centimeters per second or even less, a pace that would barely register as a whisper of movement at the surface. Yet over geological timescales, this slow, persistent flow transports immense volumes of water, influencing the climate of the entire globe. As this deep water slowly circulates through the ocean basins, it gradually warms and mixes with less dense waters, eventually beginning a slow, diffuse ascent or upwelling towards the surface in other parts of the world, often in regions of the Pacific and Indian Oceans. This upwelled water brings with it a rich bounty of nutrients that have accumulated in the deep, fueling the productivity of surface ecosystems. The cycle then completes as this warmed, less dense water eventually cools and becomes more saline again, ready to begin its deep descent anew, a continuous, vast and silent planetary heartbeat. The full journey for a parcel of water within this great conveyor belt can take anywhere from 500 to 2,000 years, a testament to the sheer scale and profound slowness of Earth's internal liquid clockwork. The Mariana Trench, however, presents a unique challenge to this grand global circulation. Its extreme depth, plunging to nearly 11,000 meters, places it well below the main arteries of the thermohaline circulation. The global conveyor belt, while reaching abyssal depths, typically flows over the vast abyssal plains at depths of 3,000 to 6,000 meters. The trench therefore acts as a profound cul-de-sac, a deep, narrow incision that largely isolates its deepest floor from the direct sweeping flow of the major deep ocean currents. This isolation contributes to the trench's role as a natural trap, a repository where accumulated materials are less likely to be swept away or redistributed by powerful flows. Nevertheless, even within the trench water is not entirely stagnant. Localized weaker currents do exist, driven by a complex interplay of factors. Tidal forces, though subtle at such depths, can induce slow, oscillatory movements of water. The topography of the trench itself, with its steep walls and complex bathymetry, can create localized eddies and recirculation patterns. Scientists using highly sensitive current meters and deploying tracers have observed these slow internal movements which, while far less vigorous than the global conveyor, are still significant over long timescales. These subtle currents can gently stir the water, resuspending fine sediments from the trench floor and slowly transporting dissolved oxygen and nutrients to the benthic communities. Even at just a few millimeters per second, these patient flows can carry microscopic particles for kilometers over the course of days or weeks, subtly influencing the distribution of marine snow and other falling debris. The interaction of deep ocean currents with the trench also plays a role in the lateral transport of materials before they descend to the very deepest points. Objects floating or suspended in the upper and mid-water columns, whether they are patches of marine snow, drifting microplastics, or even larger debris, can be carried horizontally by these currents for vast distances. A plastic bottle discarded off the coast of Japan, for instance, might be swept by surface currents across the Pacific, then slowly sink into the mesopelagic zone where it could be picked up by slower, deeper currents, carrying it towards the general vicinity of the Mariana Trench. Only when its density finally overcomes all buoyancy and drag does gravity take over, pulling it vertically into the trench's deepest embrace. Thus, deep currents act as a vast, slow-motion sorting and delivery system, bringing a diverse array of materials, both natural and anthropogenic, from distant sources towards the trench's gravitational funnel. The presence and movement of these deep currents are also crucial for the life that thrives in the abyss. Although food is scarce, dissolved, oxygen is vital for the metabolic processes of most deep-sea organisms. The cold, dense water formed at the poles is exceptionally rich in dissolved oxygen, because gases are more soluble in colder water. As this oxygen-rich water sinks and spreads across the abyssal plains, it acts as a life-sustaining breath for the deep ocean. Even the slow, localized currents within the trench help to replenish the oxygen supply, preventing anoxic conditions that would render the environment uninhabitable for many forms of life. Without this continuous, albeit slow, delivery of oxygen, the unique ecosystems of the trench, adapted to extreme pressure and cold, would struggle to survive. Furthermore, deep ocean currents also play a role in the long-term distribution of pollutants, particularly microplastics and persistent organic pollutants. While the trench itself is a sink, the currents leading into its vicinity can effectively disperse these contaminants across vast areas. Microplastic particles, once reaching a neutral buoyancy level in the water column, can be transported horizontally for hundreds or thousands of kilometers before finally settling. This means that plastic debris found in the Mariana Trench may not necessarily originate from nearby landmasses, but could be a silent traveler from distant continents, carried by the invisible pathways of the deep ocean. The currents act as a global transport network, connecting even the most remote corners of the ocean to the sources of human impact. Studying these deep ocean currents is an immense scientific challenge. Their extreme slowness, the vast depths at which they operate, and the sheer scale of the ocean make direct observation incredibly difficult. Oceanographers employ specialized instruments such as moored current meters, which sit on the seafloor or are suspended in the water column for months or even years, patiently recording the subtle movements of the water. They also use chemical tracers like chlorofluorocarbons CFCs, or specific isotopes which were introduced into the atmosphere by human activity and then absorbed by the ocean. By mapping the distribution of these traces at different depths, scientists can infer the pathways and timescales of deep water circulation, piecing together the invisible tapestry of the ocean's slow internal movements. Ultimately, the deep ocean currents, this silent conveyor, represent another layer of complexity in understanding what falls into the Mariana Trench. They are the unseen hands that guide, distribute, and sometimes concentrate the countless particles and objects that begin their long descent. While the trench's deepest points may be largely isolated from the main flow of the thermohaline circulation, the surrounding deep currents continually feed material into its broader catchment area, ensuring a steady, if sparse, influx. As this patient global circulation continues its ancient rhythm, transporting the breath of life and the echoes of humanity across the silent abyssal plains, it reinforces the profound interconnectedness of our planet, binding the polar ice caps to the deepest, darkest trenches in a ceaseless, slow-motion dance of water and gravity. The enigma of unidentified objects. As the silent conveyor of deep ocean currents performs its patient global circulation, carrying the breath of life and the subtle whispers of distant lands into the profound abyssal plains, even the most advanced human instruments occasionally encounter phenomena that defy immediate classifications. These are the unseen spectres, the enigmatic objects that emerge from the perpetual darkness of the Mariana Trench, challenging our understanding, hinting at secrets yet to be deciphered, and reminding us that even in our era of unprecedented exploration, the deepest parts of our world remain a frontier of profound mystery. The very act of exploring the Mariana Trench is an exercise in grappling with the unknown. Our vision is limited to the narrow cone of light cast by a submersible's powerful lamps, piercing a darkness so absolute it absorbs all photons. Our sensors gather data from a world under unimaginable pressure, where familiar forms can be distorted and where the alien nature of the environment itself can render even common objects unrecognizable. Thus, when remotely operated vehicles or human-occupied submersibles capture an image or detect a signal that does not conform to known geological structures, biological organisms, or identifiable human debris, it opens a chasm of scientific intrigue. These fleeting glimpses, often blurry or incomplete, become points of intense scrutiny, prompting questions that echo in the silent void of the deep. One category of these enigmatic observations includes geological formations that seem to defy conventional explanation. The seafloor of the trench is not a smooth, uniform plain. It is a landscape of immense complexity sculpted by tectonic forces, volcanic activity, and the slow accumulation of sediment. Sometimes, however, an ROV might glide over a rock structure, a mineral deposit, or a peculiar arrangement of formations that does not immediately align with known geological processes of subduction zones or deep-sea volcanism. Perhaps a perfectly geometric protrusion, seemingly too regular for natural erosion, or an unusual mineral crystallization unlike any previously catalogued. Scientists in such instances must cautiously analyze the data, comparing it with extensive geological databases simulating formation processes and acknowledging the possibility of entirely new mineral structures or unprecedented geological phenomena that are unique to the extreme conditions of the trench. The immense pressures and the unique chemical environment might indeed foster geological processes and mineral formations that are utterly unlike anything observed in shallower, more accessible parts of the Earth's crust. Then there are the biological enigmas, the living spectres that occasionally drift into view, startling in their unfamiliarity. Despite the incredible discoveries of new deep-sea species with every expedition, the ocean's biodiversity remains largely uncharted, especially in the Hadal zone, the deepest parts of the trenches. An ROV camera might capture the fleeting image of a creature that exhibits an unknown morphology, a swimming pattern unlike any described, or a bioluminescent display of uncatalogued complexity. Perhaps a translucent form moving with an unsettling grace, or a creature whose size and shape challenge the very limits of what scientists believe can exist under such extreme pressure and scarcity of food. These observations are rarely definitive. They are often glimpses, quick flashes of movement or indistinct shapes in the periphery of a camera's view. But each such sighting fuels the scientific imagination, driving further exploration, the hope of eventually capturing and classifying these truly alien forms of life that have evolved in profound isolation. Beyond the natural world, humanity's own impact on the deep ocean can create its own category of unidentified objects. While we have discussed the clear presence of plastic and recognizable sunken legacies like shipwrecks, there are also instances of highly degraded, fragmented, or unusually constructed human-made debris that resists easy identification. A piece of metal corroded beyond recognition, its original form and purpose lost to the relentless work of time and deep-sea processes. A synthetic material, perhaps from an experimental aircraft, or an uncatalogued military test, whose unique composition or unusual degradation patterns make it difficult to trace. These objects, once identifiable parts of our technological world, become anonymous fragments in the deep, their stories erased by the ocean's vast, patient power. They are ghosts of our own making, lingering in the abyss, silently challenging our ability to catalogue and comprehend our full footprint on the planet. The allure of the truly unexplained, however, often leads the human imagination beyond the realm of known geology, biology, and human technology. There is a primal fascination with the idea of something entirely foreign, something not of this earth, finding its way to these ultimate depths. Stories and theories fueled by fleeting observations or ambiguous data sometimes emerge, suggesting the possibility of extraterrestrial objects, or even evidence of previously unknown, highly advanced civilizations. For instance, the discovery of highly unusual metallic spheres on the sea floor in certain regions, or the detection of anomalous seismic signals that do not fit typical earthquake patterns, can ignite such speculation. However, it is crucial to approach these possibilities with rigorous scientific skepticism. The vast majority of unidentified phenomena, upon closer inspection or with further data, are eventually explained by natural processes, by the discovery of new species, or by the identification of known human objects in unexpected states of degradation. The ocean, particularly its deep and unexplored regions, is already alien enough without invoking external origins. Scientists investigating these unseen spectres employ a methodical and patient approach. The first step is always to gather more data. This means repeated submersible dives to the same location, deploying advanced imaging sonar, high-resolution cameras, and sensitive chemical sensors. Artificial intelligence and machine learning algorithms are increasingly being used to analyze vast datasets of seafloor imagery, searching for patterns and anomalies that human eyes might miss. The goal is to move from a single ambiguous observation to a robust, multifaceted dataset that can support a definitive identification. If an object is truly anomalous, attempts might be made to collect samples using the manipulator arms of an ROV, bringing it to the surface for detailed laboratory analysis, where its chemical composition, crystalline structure, and isotopic signatures can be meticulously examined. Such analyses can reveal whether the material is natural or synthetic, its age, and even its potential origin. The challenge of identifying these objects is compounded by the sheer scale of the Mariana Trench itself. Its immense length and depth mean that only tiny fractions of its floor have ever been directly observed or sampled. What we have seen is merely a scattering of pinpricks in a vast, dark canvas. For every square meter we have explored, there are countless square kilometers that remain utterly unknown, holding untold geological wonders, undiscovered life forms, and perhaps indeed, truly enigmatic objects that await their moment of revelation. This vastness of the unexplored is itself a powerful generator of mystery, a fertile ground for the imagination to wander. Ultimately, the enigma of unidentified objects in the Mariana Trench is a reflection of our continuous journey into the unknown. It is a testament to the fact that even on our own planet there are still profound frontiers, places where the familiar gives way to the utterly alien, where the boundaries of our knowledge are constantly being pushed and redefined. These unseen spectres, whether they are new forms of life, unusual geological formations, or highly degraded fragments of human history, serve as powerful reminders of the ocean's enduring capacity for wonder and surprise. They are the quiet challenges to our understanding, the silent invitations to deepen our curiosity, and the whispered promises that the Mariana Trench, in its profound, crushing embrace, still holds secrets that patiently await their slow, gentle unveiling, perhaps even in our deepest dreams. Tools of deep-sea discovery. From the tantalizing glimpses of unseen spectres that drift through the profound darkness, hinting at secrets yet unveiled, arises the human imperative to understand, to reach, and to illuminate. Probing the void of the Mariana Trench, an environment designed by nature to resist intrusion, demands ingenuity, patience, and the development of specialized tools of deep-sea discovery. These are not mere machines, but extensions of human curiosity crafted to withstand the crushing embrace, to pierce the eternal night, and to gather the whispers of a world utterly alien to our own, slowly, meticulously bringing its mysteries into the light of scientific understanding. Our earliest attempts to fathom the deep were rudimentary yet revolutionary for their time. As previously mentioned, the HMS Challenger expedition in the late 19th century deployed weighted sounding lines, long ropes with heavy lead weights, painstakingly lowering them into the abyss. This manual, laborious process, taking hours for a single measurement, provided the first quantitative hints of the trench's immense depth, marking the initial tentative steps into the unknown. These were the simplest of tools, yet they laid the conceptual groundwork for all subsequent exploration, demonstrating humanity's persistent desire to measure and comprehend the unseen. The true revolution in deep-sea measurement arrived with acoustics. The development of sonar technology, initially for military applications, transformed our ability to map the seafloor. Instead of a single-point measurement multi-beam, sonar systems mounted on surface vessels send out fan-shaped arrays of sound waves. These sound waves travel through the water, bounce off the seafloor, and return as echoes. By precisely measuring the time it takes for these echoes to return, and knowing the speed of sound in water, scientists can create incredibly detailed three-dimensional topographical maps of the ocean floor. This acoustic mapping has allowed us to visualize the trench's complex bathymetry, its steep walls, its internal basins, and its deepest points, like the Challenger Deep, revealing a landscape far more intricate than anyone could have imagined from simple-sounding lines. It is like feeling the shape of a hidden mountain range, with sound slowly building a picture in the mind's eye. However, mapping from the surface, while invaluable, cannot provide the intimate, up-close observations necessary to truly understand the trench. For this, humanity developed submersibles vehicles designed to carry humans or instruments into the crushing embrace. The earliest deep-diving submersibles, like the bathyscaphe Trieste, were pioneering feats of engineering. In 1960, the Trieste, commanded by Jacques Picard and Don Walsh, made history by successfully descending to the very bottom of the Challenger Deep. This colossal vehicle, designed with a thick steel sphere for its crew and filled with gasoline for buoyancy, demonstrated that human-designed craft could indeed withstand the unimaginable pressures. It was a brief yet profound visit, offering a fleeting glimpse of the abyssal floor, a moment of direct human presence in a truly alien world. Following the Trieste's heroic descent, the focus shifted towards unmanned vehicles, recognizing the inherent risks and complexities of human-occupied dives to such extreme depths. Remotely operated vehicles, or ROVs, became the workhorses of deep-sea exploration. These tethered robots, controlled by operators on a surface vessel through fiber optic cables, can carry an array of sophisticated sensors and tools. They are equipped with high-definition cameras, powerful lights to pierce the perpetual darkness, sonar systems for localized mapping, and robotic manipulator arms capable of collecting rock sediment and biological samples. The tether provides not only control signals, but also power, allowing for extended missions. ROVs have revolutionized our ability to observe, sample, and conduct experiments directly on the trench floor, revealing the intricate life forms, the geological features, and the pervasive human debris, including plastics, that accumulate there. Complementing ROVs are autonomous underwater vehicles, or AUVs. Unlike ROVs, AUVs are untethered, pre-programmed to follow specific paths and collect data independently. They carry their own power sources and data storage, allowing them to explore vast areas of the seafloor for extended periods without direct human intervention. While they lack the real-time control and direct sampling capabilities of ROVs, their ability to cover large distances and conduct systematic surveys makes them invaluable for mapping, detecting anomalies, and gathering broad-scale oceanographic data. Imagine a silent, independent explorer gliding through the darkness, patiently gathering information, a tireless scout in the vast unknown. For truly extreme depths like the Challenger Deep, specialized landers have proven particularly effective. These are unmanned, free-falling platforms, often equipped with cameras, light sensors, and baited traps. They are deployed from a surface vessel, slowly sinking to the seafloor, where they conduct their scientific mission for hours or days. When their mission is complete, they release ballast weights and float back to the surface, often aided by acoustic signals. Landers are less complex and less expensive than full submersibles, making them ideal for long-duration deployments and for reaching the very deepest points repeatedly. They have been instrumental in capturing images of Hadal Zone life, collecting samples of amphipods, and deploying environmental sensors to measure temperature, pressure, and chemical parameters directly on the trench floor. The sensors themselves are masterpieces of engineering designed to function under conditions that would destroy conventional electronics. Pressure housings must be meticulously crafted from high-strength titanium or specialized ceramics. Electronic components must be miniaturized and shielded. Cameras are equipped with incredibly sensitive low-light sensors and robust housings. Chemical sensors designed to detect subtle variations in pH, oxygen, or nutrient levels must operate with precision under extreme compression. Acoustic sensors used for navigation, communication, and sub-bottom profiling must be finely tuned to the unique properties of sound propagation in deep water. Each tool, from the simplest temperature probe to the most complex mass spectrometer, represents a triumph of materials science and precision engineering, a testament to humanity's drive to overcome the natural barriers of our planet. The data gathered by these tools is immense and complex. High-resolution imagery sonar scans, environmental sensor readings, and biological samples all contribute to a growing multi-layered understanding of the Mariana Trench. Scientists use advanced computational models to process this data, creating virtual representations of the trench, simulating its geological processes and modeling its unique ecosystems. Machine learning algorithms are now being trained to identify species from images, to detect subtle changes in the sea floor, and even to flag potential unseen specters that warrant further investigation. This integration of advanced hardware with cutting-edge software allows us to extract ever more profound insights from the limited observations we can make in such a remote and challenging environment. Yet, despite these incredible technological advancements, the Mariana Trench remains largely unexplored. The vastness of its length, the sheer scale of its depth, and the immense cost and logistical challenges of deep-sea exploration mean that only tiny fractions of its abyssal floor have ever been directly observed. Each expedition is a monumental undertaking, a testament to human perseverance and scientific collaboration. The tools of deep-sea discovery are constantly evolving, becoming more resilient, more autonomous, and more capable, pushing the boundaries of what is possible in this extreme realm. They are our eyes and hands in the darkness, our patient probes into the void, slowly unveiling the secrets held within Earth's deepest cradle. And as these silent explorers continue their tireless work, they bring us ever closer to a comprehensive understanding of what falls into and what resides within the crushing, mysterious embrace of the Mariana Trench. A deep-sea legacy. The Mariana Trench, far from being a static monument to depth, is a dynamic, ever-evolving frontier, a profound testament to Earth's ceaseless geological rhythms and increasingly to humanity's indelible mark. As our current tools probe its immense void, their very success ignites a vision of what future generations might achieve, and what enduring legacy this abyssal cradle will hold, not just for scientific understanding, but for the very narrative of our planet. Its future is a tapestry woven from deep time and fleeting human impact, a story that continues to unfold in the profound silence. The colossal dance of tectonic plates which birthed this abyssal cradle will continue its slow, inexorable rhythm for millions of years into the future. The immense Pacific Plate will persist in its patient grinding descent beneath the Mariana Plate, deepening the trench millimeter by slow millimeter. This ongoing subduction will ensure the trench remains the deepest point on Earth, a perpetual geological funnel. With this subduction will come the continued deep geological breath of our planet, the release of superheated water from the descending slab, fueling the generation of magma and giving rise to the volcanic eruptions that build and reshape the Mariana Islands. The profound stresses and strains within Earth's crust will continue to manifest as earthquakes, some of them of immense power, reminding us of the planet's internal restless energy. The trench, therefore, will remain a zone of intense geological activity, a living, breathing scar on our planet's face, constantly being reworked by forces beyond human comprehension or control. Within this geologically active future, the natural processes of accumulation will also persist. The gentle, organic rain of marine snow will continue its eternal descent from the sunlit surface, carrying nutrients and carbon to the starved ecosystems of the abyss. Layer upon layer of fine sediment composed of microscopic skeletal remains and decomposed organic matter will slowly accumulate, building up the trench floor, compressing older layers into solid rock over geological timescales. Rare colossal whale falls will still occur, providing episodic feasts that temporarily transform the local abyssal communities, only to slowly fade into the sediment, leaving behind their massive, enduring skeletal remains. These natural cycles spanning millions of years will continue to write the Earth's deep time history into the very fabric of the trench, a silent, patient chronicle of life and geological change. However, a new and increasingly dominant layer will also continue its relentless descent, the synthetic snowfall of our age. Plastic debris, from recognizable macroplastics to the insidious, invisible micro and nanoplastics, will continue to accumulate in the trench. These enduring polymers, designed for fleeting human convenience, will become geological markers compressed into the forming rock, a permanent, undeniable stratum of the Anthropocene. Unlike natural materials which largely degrade and recycle, plastics will persist for millennia, perhaps even hundreds of millions of years, slowly becoming an integral, if incongruous, part of the deep sea legacy. Scientists believe that as plastics continue to fragment under the extreme pressure and cold, they may become even more pervasive at the microbial level, ingested by a wider range of deep-sea organisms with long-term ecological consequences that we are only beginning to understand. The chemical additives within these plastics will continue to leach into the abyssal waters, subtly altering the chemical environment and potentially impacting the unique physiology of Hadal organisms. The trench, therefore, will not only be a natural archive, but also a profound deep-sea landfill, a permanent repository for the waste of our industrial civilization. The future of exploration within the Mariana Trench will undoubtedly involve even more sophisticated tools of deep-sea discovery. Current ROVs and AUVs, while remarkable, represent only the beginning. Future generations of submersibles may incorporate advanced artificial intelligence, allowing for greater autonomy and real-time decision-making in navigating the complex abyssal terrain. Bio-inspired robotics, drawing lessons from the incredible adaptations of deep-sea life, might lead to soft-bodied, pressure-resistant vehicles, capable of more delicate interaction with fragile ecosystems. Swarms of tiny, networked autonomous sensors could be deployed, blanketing vast areas of the trench, gathering unprecedented volumes of data on currents, chemistry and biological activity, painting a far more comprehensive picture of this alien world. The integration of genetic sequencing technologies directly into deep-sea probes will allow for on-site identification of new species and the study of microbial communities with unparalleled detail, transforming our understanding of life's limits. These technological advancements will slowly, methodically peel back the layers of mystery, revealing more of the trench's hidden wonders. Recognizing its unique status, international efforts are slowly coalescing to safeguard these profound depths. The Mariana Trench, along with other deep-sea trenches, is a designated part of the Mariana Trench Marine National Monument, established by the United States, providing a degree of protection. However, the future will demand even broader international cooperation and more robust conservation strategies. As technology advances, the potential for deep-sea resource extraction, such as mining for valuable minerals from hydrothermal vents or polymetallic nodules, might become economically viable in other abyssal environments. While direct mining in the Challenger Deep itself is currently unthinkable, due to the extreme conditions the precedent set in other deep-sea areas, could pose future threats to the broader trench environment, disrupting fragile ecosystems and potentially releasing ancient trapped sediments and pollutants. Therefore, the trench's future legacy will also hinge on our collective commitment to its protection, acknowledging its irreplaceable value as a scientific laboratory, a unique ecosystem, and a natural archive rather than merely a resource to be exploited. Ultimately, the Mariana Trench will continue its silent ancient work, an eternal archive of both planetary processes and the fleeting yet impactful presence of humanity. The geological clock will continue to turn slowly, subducting crustal material, recycling it back into the Earth's mantle, a process that will eventually consume even the most durable of our plastics, albeit over unimaginably vast timescales. The unique life forms adapted to their crushing embrace will continue their slow dance of survival, evolving and adapting to the subtle shifts in their environment. And for humanity, the trench will remain a profound symbol, a testament to the Earth's enduring power, a stark reminder of our own footprint, and a boundless source of wonder forever holding its deep-sea legacy within its crushing patient embrace, whispering its secrets to those who dare to listen. And so as we gently drift away from the profound, silent depths of the Mariana Trench, our journey through its crushing embrace and its myriad accumulations slowly, softly draws to a close. Like the final, lingering light of a sunset, fading beneath the horizon or the vast, slow ebb of a deep ocean current. Receding into the unseen, our exploration now recedes, leaving behind only the tranquil resonance of knowledge. In the immense dark quiet of the trench, countless stories settle into the sediment, becoming part of Earth's enduring memory, held in a profound, patient stillness. So too, as your own consciousness now softens, allow your thoughts to drift downwards, settling into the tranquil depths of your mind. May the profound stillness of the abyss, a place where all things eventually find their rest, now envelop you, inviting a sleep as deep and undisturbed as the ocean's floor, where only the softest whispers of distant dreams may reach. May the ancient, patient silence of the trench cradle your slumber, guiding you to a serene and restorative night. Good night.